Good morning, everyone. Good to see you all. Very happy to have Florent Baudier from Texas A&M, and he's speaking on Umbel convexity and the geometry of trees. Florent?
All right, thank you, Benjamin, for the introduction. So in this talk, I want to discuss a joint work with Chris Gartman from Texas A&M University. And so we were concerned about finding a metric invariant that would capture the geometry of contably branching trees, and that would give us some quantitative estimates on distortion, lower bound, compression rate bonds of coarse embedding, and maybe also to be able to find new classes of Banach spaces that we can characterize in purely metric terms. Okay. So that was a tall order, but I think we partially succeeded. And our inspiration came from the linear theory and actually the geometry of binary trees, and in particular the Markov convexity invariant that was introduced by Linauer and Perez in 2006. So let me first recall a little bit of the linear theory, and then I'll move on to the joint work with Chris, and hopefully I'll have time to talk a little bit about embedding trees into Heisenberg groups. Right. So the geometry of binary trees. So there is this very important and famous theorem of Bourgain, which is a metric characterization of superreflexivity. So Bourgain showed that a Banach space is superreflexive if and only if you do not contain the binary trees. Okay, so BKs is the binary tree of height k. So this is a picture of B3. So this is a combinatorial tree, and you equip this graph with the graph distance. So you get a metric space. And this parameter here, it's the Y distortion of the BK, and it's defined as follows. So given two metric spaces, arbitrary metric spaces X and Y, you can try to understand how well you can embed X into Y in a Baudier fashion. Okay. So what you do it is you're looking at all the maps, the injective maps from X into Y. You compute the Lipschitz constant of F, which is this quantity here, the Lipschitz constant of the inverse. You multiply, you get the distortion of the embedding. It tells you how the distances are, the pairwise distances are distorted, and then you infer all the possible Lipschitz embeddings. Okay. So this parameter here tells you how well you can embed X into Y. Okay. So what Bourgain tells you is that in a superreflexive Banach space, the distortion incurred when embedding a binary tree of height k has to blow up to infinity. Okay. So superreflexivity, it's a local property of Banach spaces, so it's a linear property. But this statement here is a purely metric statement. Okay. So you have a purely metric characterization of a linear property, and this is one of the main research venue in the Rebbe program, and this was one of essentially the first step in the Rebbe program. Okay, so today I will be mostly interested in understanding the rate of growth here. Okay, so it goes to infinity, but how fast does it go to infinity? Can I estimate this in terms of maybe the size, the height of the tree? Okay, so to do that, and this was already included in Bourgain's proof, you need superreflexivity is not the right notion to work with. You need a geometric reformulation of superreflexivity. And this was known since the 70s due to the work of Enflo and later Pizier. So Enflo told us that, well, superreflexive Banach spaces are Banach spaces that emit an equivalent norm that is uniformly convex. Okay, and by duality, uniformly smooth. Okay. Now, what Pizier showed is a quantitative refinement of Enflo's renorming, and this was really a truly a very deep result, and a lot of things came out of this renorming theorem here. So he said that if the Banach space has an equivalent norm that is uniformly convex, then it must have one that is Q uniformly convex. So where Q uniformly convex means that the modulus of uniform convexity is of power type Q. So it means that it at least some power of T, okay, if T is the separation parameter in the modulus, okay? And so this part here is really what would be of interest to us today. And that's what Bourgain was using. So how did Bourgain prove the non-embeddability part in his metric characterization? Well, he showed the following inequality. So that is, he showed that this inequality here is valid in any Q uniformly convex Banach space. So what is this inequality about? So you look at the binary tree of height to K, and you look at a map of this tree into X, okay? And you show that, well, you take these minimums here, and then two averages here. So what this inequality tells you is the following thing. So you have these two vertices here in your tree. So the vertex epsilon delta and epsilon delta prime, which are here. And how these vertices are chosen. So first, you pick a scale S, okay? Then you pick a level, which is between the height 2 to the S and 2 to the K minus S, so just some portion of the tree here. And then there is epsilon, is it at level L? So this is, I mean, you index the vertices of the binary tree by negative 1, 1 vectors. And so you have this fork in your tree, and when you average over all possible choices of delta, which are, so here you take points that are 2 to the S levels above the vertex epsilon. So this quantity here tells you that there is a scale, there is a level, there is a vector here, such that on average, when you take the average of the distance between the images of this, the tip of the fork, properly rescaled, this is less than C times K to the negative 1 over Q times Lipschitz constant of F, okay? So here, the trivial inequality is you get this inequality with C equals 2 and nothing here. Because if F is Lipschitz, this quantity is going to be less than the distance between epsilon delta and epsilon delta prime. But the distance between these two guys here is 2 to the S plus 1. Okay, so when you rescale by 2 to the S, you just get 2 and nothing there. So the fact that you have this K to the negative 1 over Q here is a significant improvement of the trivial inequality that you get. Okay. And once you get this inequality, okay, what is absolutely straightforward is to show this distortion lower bound on the to embed the binary trees into a Q uniformly convex Banach space. Okay, so this inequality here is completely immediate from this inequality there. So the problem is not to prove this. The problem is to show that the inequality is actually satisfied for some spaces. And what Bourgain did is show that this inequality is valid when the Banach space is Q uniformly convex. Okay. And the way he did that, he used the fact that Q uniformly convex Banach spaces, they have martingale cotype Q, so which is a notion that was introduced by Gilles Pizier in his renorming theorem. And Bourgain exploited the natural connection between binary trees and the Walsh-Paley dyadic martingales. Okay. So now, of course, here, this inequality only uses distance between pair of points. So this makes sense in a purely metric space. And well, you would get the same distortion if this inequality is satisfied in an arbitrary metric space. Okay. So now, Bourgain's inequality doesn't tell you anything for weaker notion of embeddings. Okay, so if you're looking at coarse embeddings of trees, it would not tell you anything. Okay, and Romain Teixeira, who was interested in coarse embeddings of groups into Banach spaces, went back to Bourgain's proof and actually observed that, well, the same proof gives something much stronger, which is this inequality here. So what is the difference between this inequality and the previous one? So in the previous one, you had a minimum here instead of an expectation, but this is not a big change. The main difference is that here you take a sum over all the scales. And in the previous inequality, we were minimizing over the scales. Okay. Now, when you have a sum over the scales, and you have to modify slightly this part here, but when you have a sum over the scales, what you get is estimates for the compression rates when you try to coarsely embed trees into Banach spaces. Okay, so this is not difficult to show that if this inequality holds here, then you can say the following thing. So now assume that you have a map from B of height 2 to the k into a Banach space Y, which satisfies this inequality. And that the map does the following. So it's a one Lipschitz map. And the lower bound here, it's a much weaker lower bound. You just want to find a function that will control the lower bound here. Okay, not just the distance over some constant. And once you have this inequality here, what you can show is that this function here, the compression function, has to satisfy this inequality here. Okay, I mean this condition here. So this rules out not only by Lipschitz embedding, but also coarse embedding with certain compression bonds. So if you take the function rho of t to be t over, I don't know, log of t, log t, something like this, so this would not be allowed. Okay, so it rules out much weaker notions of embeddings. Okay. So now Markov convexity. So Markov convexity is a delicate metric invariant that was introduced by Linauer and Perez in 2006. And so here is the definition. So might be a lot to take in if you have never seen that. So let me try at least to give you a rough idea of what this inequality is about. So you have a metric space, okay? And we say that the metric space is Markov Q convex if the following happens. So you're looking at Markov chains taking values on a state space omega, and you look at a map from omega into X. So this is your space X, your metric space X. You have a state space here where Markov chains takes their value in, and you have a map in between. Okay. Now you take a Markov chain and you let this Markov chain evolve. So this is WT up to time t. And then you look at another Markov chain that behaves as follows. So first, you pick a scale, and this second Markov chain here, W tilde, evolves exactly the same as WT until time t minus 2 to the s. And after this time, just evolves independently, but according to the same transition probability. Okay. So when you do this, you create a fork in your state space. And then you look at the image of the two endpoints here. So you end up here and here in your metric space. You can compute the distance between these 2 points. You raise to the q, rescale properly, and then you take an average because here you have stochastic processing. Okay, you do this for every time, for every scaling factor, you sum and you get a quantity. Okay, and on the right-hand side, what you're looking at is the distance between the images of 2 positions in the random walk. But just with a unit increment of time, okay? And you take the sum over all the times, and if this quantity here is less than some constant times this quantity there, you say that the space is Markov Q convex, okay? So, well, based on the definition, it seems clear that it might not be that easy to compute this invariant, but this invariant is extremely powerful. And in particular, what it does, it gives you the following lower bound for the distortion of embedding the binary trees into a Markov Q convex space, okay? And this is, again, log of k to the 1 over q. Now, it might not be completely obvious why this gives you that. The reason is, well, first, Markov convexity is a bi-Lipschitz invariant. This is clear from the definition. And to show that you have this distortion lower bound here, you need to show that the best Markov convexity constant in this inequality here is at least log of k to the 1 over q. And this is true because if you take omega to be the binary tree, x will be the binary tree, and f the identity function, you take the Markov chain to be the directed random walk on the tree, okay? And this gives you almost immediately that you have this lower bound there. Okay. So Now, one of the main results about Markov convexity is the following. So remember, Bourgain gave a characterization of having an equivalent num being uniformly convex in terms of not containing the binary trees. Now here, what Linauer and Perez and later Mendel and Nauer did is they say, okay, fix Q, okay, and look at the class of Banach spaces that have an equivalent norm that is Q uniformly convex. Okay, now Q is fixed. Can we find a purely metric characterization of this class? And the answer is yes, and Markov convexity does that. Okay, so again, you have a class of Banach spaces defined in terms of a local notion, and here this is a purely metric statement. Okay, so in the first paper, they proved this implication here that every Q uniformly convex Banach space is Markov Q convex, and the proof they had is similar to Bourgain's proof using martingale Cotype. And they were not able quite to prove the converse here. They had a weaker statements, but in the paper of Manor and Asaf, they were able to actually show that if you Markov Q convex, then there is a renorming that is Q uniformly convex. Okay. All right. And they also gave a different proof of the first implication, and I will get back to this later because for us it was important that the new approach that they used. All right. Now, what about the geometry of Cantabile branching trees? Well, the Cantabile branching trees are, well, as their name indicate, Cantabile branching versions of the binary trees. So the difference is instead of having only two descendants, here you have Cantabile many, right? So at every level, you have Cantabile many vertices, right? And one way to code this graph is to look at, so this is the set of at most k subsets of n. So you will index the root by the empty set. This you will index this by the integer, and then by pairs of integers, and so on and so forth. Okay, and you equip this with the tree metric. All right. So what do we know about the Cantabile branching trees? So about 10 years ago, with Nigel Carlton and Gilles Lancien, we were able to prove what can be think of an analog of Bourgain's metric characterization, but in the asymptotic setting, okay? And we proved the following thing. So first, assume that your Banach space is reflexive, okay? So I work in the reflexive setting. Then what we could show is that a Banach space has an equivalent norm that is asymptotically uniformly convex and asymptotically uniformly smooth, if and only if you do not contain the Cantabile branching trees, okay? So now we know in the asymptotic setting that asymptotic uniform smoothness or asymptotic uniform convexity alone are not sufficient to provide obstruction, because every tree embeds into little L1, and every tree embeds into C0, like every separable metric space does. But L1 is the most asymptotically uniformly convex space, and C0 is the most asymptotically uniformly smooth. So alone, these two notions are not sufficient to provide an obstruction, okay? But when you combine them, then you get an obstruction to the bi-Lipschitz embeddability of Cantabile branching trees. And one interesting example, and actually the prototypical example of a Banach space that is reflexive, AUS and AUC, is an LP sum, so P in the reflexive range, of finite dimensional spaces. Okay, so these asymptotic notions of convexity and smoothness, they do not see the local behavior of your Banach space. So this space here is interesting because since it contains the L infinity ends, it will contain every finite metric space. So in particular, it will contain the binary trees. However, it does not contain the Cantabile branching trees. Okay. Now there is a subtlety here, which is the following. So could we put reflexivity inside the statement there? Okay. Well, it was open for a while until Yoel Perrault said, well, no, you can't because of gem space. So gem space is non-reflexive, it is, it is AUS and AUCable, and yet you do not contain the Cotype branching trees, okay? So you cannot put reflexivity inside the statement here, okay? So I'll get back to this subtlety a little bit later. Right, any questions so far? So now, what about the rate of growth here? Okay, because this is my main concern today. So the technique that we use to show that it does not embed, first, it's of bi-Lipschitz nature. It will not tell you anything for weaker notion of embeddings. And quantitatively, it's not optimal. And the reason is, well, you have these two notions, okay? And each notion comes with its own modulus, right? Modulus has power type, but so yeah, and this, when you try to find distortion lower bounds here, it gives you something, but actually it gives you something suboptimal, okay? So it's not really the right way to obtain very tight estimate for distortion bonds, and it's not going to tell you anything about compression rates of coarse embeddings. So fortunately, in a beautiful work of Lima and Randriana Rivoni, they used Rowlevich property beta, okay, to solve some nonlinear problem in Banach space theory, okay. And what is this property beta? So this is Denka-Skutsarova's definition, okay? So it's another way to generalize uniform convexity in the asymptotic setting, but in a different direction than asymptotic uniform convexity does. And for us, and for the geometry of Cotype branching tree, this is really the notion you want to work with, okay? So what does this notion says? So it says the following. So it looks very much like uniform convexity. So it says that if you take a point in the unit ball of your Banach space and a sequence in the unit ball that is T separated, where T is some positive number, okay, then there always exists some element in the sequence such that the midpoint between W and Xi naught is way inside the ball, okay, and in a uniform fashion, so it does not depend on W or the sequence, just on the separating parameter, okay. Now, this is obviously an infinite dimensional notion because there is no such thing as a separated infinite sequence in a finite dimensional space. So it will escape finite dimensional phenomenon. And if you want some intuition, okay, I'm going to try to give you the intuition on a two-dimensional picture because that's the only thing I can draw. But the intuition, I think, is the following. So if you take a point on the unit sphere and then a sequence of points here on the unit sphere that are separated, if you have enough points in your sequence, well, you cannot pack all of them on this side of your cube here, where here, if you take midpoints between this and this, it will stay on the sphere. So it has to escape to the other dimensions, okay? And when you escape to the other dimensions, then of course, you have midpoints that are way inside the sphere, okay? And we say that a Banach space has property beta with sporer type P if the modulus of beta is at least T to the power P up to some constant, okay? So it turns out that property beta is, well, it's closely related to asymptotic uniformly convex and asymptotic uniformly smooth renorming. So first, property beta implies reflexivity, okay? So when you assume that a space has property beta, you're already working in the reflexive setting. And then we know that the class of Banach spaces admitting an equivalent norm with property beta is, so first you can renorm so that it has beta with power type P, but also it's the same class as the class of reflexive Banach spaces that are AUS and AUC renormable, okay? So this actually follows from works of Denka in the 90s and the renorming theory of Nostodel and Schumprecht, but it was really observed, I mean, a little bit more recently, and it's done in this paper, for instance, okay? So So now you have the equivalence between these two classes here. Okay. Now, as I said, property beta is better if you want to understand the quantitative theory of embeddability of the Cotype branching trees. And in a paper with Sheng Zheng, we showed the following thing. So if a Banach space has property beta p, so beta with prototype p, then you have this distortion lower bound, okay, that keeps popping up for trees, log of k to the 1 over p. And the reason we could do that is because we could use the self-improvement argument that was used by Bill Johnson and Gideon Sheshman to show non-embeddability of diamond graphs or laxograph into uniformly convex spaces. And that was later used by Klutner to give a very simple proof of Bourgain's non-embeddability result. And the reason we could do this is because property beta is really the property you want to implement this self-improvement argument. Okay, it works extremely well with this property. And this bound is tight because, well, Bourgain in his metric characterization paper showed that you can embed the binary trees into L2 with distortion square root of log k, if k is the height. But actually, essentially the same proof can be extended to every piece and to Cotype branching trees as well. Okay, so it's essentially the same argument. So, and this is tight. So you get the right order of growth when trying to embed the Cotype branching trees when you use property beta. Okay. Now the problem here is that first the target space is still a Banach space, and ultimately we want to give abstractions for embeddability into arbitrary metric spaces. And the other problem is, again, this argument is very of a bi-Lipschitz nature. It does not tell you anything about weaker notions of embeddings, such as coarse embeddings or even for compression exponents. So you need to do better. And so with Grith, we came up with this new metric invariant that we called Umbel convexity. So, well, don't be scared about this this crazy expression here. I'm going to spend some time to explain what this is about. So we're looking at maps. So X is your metric space, and you're looking at maps from. So this is the Cotype branching tree of height to k, and we want this inequality to hold for some constant pi here. Okay. So what are we trying to do here? So we're trying to do the following thing. So here is your Cotype branching tree of height 2k, and you pick a scale, okay? You pick a scale S, and then you chop off your tree into slices of thickness 2 to the s plus 1, right? So, and then, so let's understand this quantity here. So what we're gonna do is, so you have that many levels, that many slices here, okay? And we're gonna pick a point at the bottom of one slice. So fix a slice and pick a point at the bottom of the slice. And then we're gonna create a fork here. So then you're gonna take a point here, a vertex that is 2 to the s levels above, where s is the scale. Then you pick a direct neighbor here that is one level above. So this is j here. And finally, you complete the fork by picking a vertex here that is at the same height as this one, right? Then you take the distance between the images of these 2 points here. So the distance between these 2 points in the treated metric, it's 2 to the s plus 1, so you rescale properly there. And what you do is you take an infimum over all possible choices of eta. Then you take a lim inf here, you push the neighbors, let's say towards the right, take an infimum over all the choices there, and take an infimum over all the possible choices here at the bottom of the level of the slice. Now you do this for every slice, you average over the slices, and then you sum for all the scales. Okay, this gives you a number, fine. And you compare this to the right-hand side. So what is the right-hand side? The right-hand side is easier. So you fix a height, okay, in your tree. So let's say that you're here, and then you look at the distance between images of these two vertices. So these vertices are edges between level L and level L minus 1, okay? And you take the supremum for level L. So this quantity here, sorry, essentially, it's the Lipschitz constant, but restricted to a certain level. Because when you have a graph and you're trying to compute the Lipschitz constant, you need to look at, you only need to look at adjacent vertices. So here we're looking at adjacent vertices, but between level L minus 1 and L. And you do this for every level, and then you average over the levels. Okay? So here we actually put as many averages as possible, because this is one problem when you want to, I mean, these invariants in the local theory, they use a lot of probabilistic tools, and they work with finite objects, so you can always take averages. I mean, you have the uniform probability on finite sets. And here in the asymptotic setting, well, you run into problems because first, you cannot take an average over, let's say, infinitely many neighbors there. And what is a random walk on a graph with unbounded degree? Okay, so these are things that are not clear, and that it's not easy to translate the probabilistic tools into the asymptotic setting. Okay, so you have to do something different, and sometimes you have to settle for less. Okay. So this is the notion of Umbel convexity, okay? So, and the main problem will be, well, okay, fine, you have an inequality, but okay, are there spaces satisfying this inequality, right? Is there an interesting class of spaces that will satisfy this inequality? And then what can you do with that? So the first thing is, so again, this is immediate from the definition of Umbel convexity. If a metric space is Umbel p-convex, then you have this distortion lower bound for the Cantabile branching trees. So this is completely immediate. And now what is maybe less immediate is that if you have a Banach space, and if your Banach space is Umbel p-convex, then the Banach space must be reflexive. Okay. So in the local theory, you don't have this problem, because in the local theory, if you do not contain the binary trees, by Bourgain's characterization, you know that the space is already super reflexive. But here, in the asymptotic setting, if you do not contain the Cantabile branching trees, because of James' space, it does not imply that the space is reflexive. So you have to show that. And this is not terribly difficult if you have the right James characterization of reflexivity. And if I go back to the inequality, to be able to prove reflexivity for us, what is very important is this lim inf here, okay? Because you can define weaker inequalities than that, but to get reflexivity, this is really what we need, okay? We need to be able to push your neighbor here towards the right, okay? And now the main result is the following. So if you have a Banach space that has property beta p, then it will be Umbel p-convex, okay? So it will satisfy this inequality, right? So you can think of this as the analog of the fact that Q uniformly convex Banach spaces, they have Markov convexity Q. They're Markov Q convex, okay? So you can think of this as the analog of this result. So I will explain a little bit how we get this. Now, when you put everything together, what you get is the Florent theorem. So, so we know that the equivalence between this and this was already known. So here, what you show is that first this implication here, well, this is just this statement there. And in fact, you can take P equals Q. Now, how do you show this implication here? So if your Banach space is Umbel p-convex, first, you know that it does not contain the Cantabile branching trees. And then you know that it's reflexive. So if it's reflexive and does not contain the Cantabile branching tree, so the BKR theorem tells you that, well, the Banach space has to have an equivalent norm that is AUS and AUC. And once you have this, then you know that there is an equivalent norm that has property beta, and you're done. Okay. Now, there is a burning question here, probably. So I said, when you go in this direction, you can take P equals Q. Okay. Now here, the equivalence only tells you that if X is Umbel P convex, then there is some Q such that your Banach space has property beta Q. Okay. And the question that you want to answer is, can I take the same value? Can I take P equals Q? Okay. Does Umbel P convexity implies having a renorming with property beta P? Okay. And this would be great because this would really be the analog of the characterization of P uniform convexity in terms of Markov convexity. So unfortunately, the answer is no. Umbel convexity does not do that. And actually, Umbel convexity cannot do that. Even though we try to prove the strongest possible inequality, because we had the renorming theorem in mind, I don't know how stronger we can be than that, okay? But there might be something else. So even though we try to prove the strongest possible inequality, this inequality cannot solve this problem of the renorming with property beta P. And the reason is the following. So Carlton gave examples of two Banach spaces, X and Y, where one has an equivalent norm with beta P, and the other one does not. And these two spaces are uniformly homeomorphic. Okay, there are two uniformly homeomorphic Banach spaces, one with beta P, the other one with no equivalent norm with beta P. So why is this a problem? This is a problem for us because Umbel convexity is stable under uniform homeomorphism. Okay. In fact, it's stable under various notions of nonlinear quotients, okay? Lipschitz quotients, uniform quotients, coarse quotients, and so on. So because of this, Umbel convexity cannot solve the problem. And in fact, if you want a metric invariant that will characterize renormings with property beta P, this metric invariant cannot be stable under uniform equivalencies of Banach spaces. And this seems like a big obstruction, okay? Now, the best thing you can hope at this point is that if your Banach space is Umbel P convex, then it admits an equivalent norm that has beta P plus epsilon for every epsilon, because that's what happens in Carlton's examples. The space doesn't have beta P, but it has beta P plus epsilon for every epsilon, okay? So there's still much to be understood here. Okay, but at least this, if you look at just the bottom equivalence here, it gives you a purely metric characterization of Banach spaces admitting an equivalent norm with property beta in terms of some Poincaré type inequality. Okay, so you still get a metric characterization of this property here. Okay. And remember, I told you the Cotype branching trees, they cannot characterize this property, but Umbel convexity does. Okay. So now there is another metric characterization of Banach spaces with property beta in terms of symmetric test space characterization in the terminology of Mikhail Ostrovsky that was given by Sheng Zheng, and that you can also find in a paper of Dilworth, Kutsarova, and Randre Narivani. It's implicit there, but you can find it. And it also follows from an Umbel convexity argument. Okay. All right. Any questions? So let me try to explain how we get that every Banach space with property beta P is Umbel P convex. Okay. So the argument to prove that Q uniformly convex Banach spaces are are Markov p-convex using martingale cotype is not something that we can really use, or at least not at this point in the asymptotic setting. But fortunately, Mendel and Auer, they gave a different proof, and the proof goes as follows. They said, well, there is a 4-point inequality, okay, the fork inequality. And so this is an inequality involving only 4 points. And if this inequality is valid, then they can upgrade this 4-point inequality to the Markov convexity inequality, the full-fledged inequality, using conditioning of Markov chains and things like that, okay? So they say, okay, just check this 4-point inequality. If you have this, then you can upgrade it to the full-fledged inequality. And for Q uniformly convex Banach spaces, this 4-point inequality follows from the parallelogram inequality for convexity. Okay. So for us, the problem is that there is no such thing as the parallelogram inequality for spaces with property beta p. Okay. But anyway, we were able to show not a 4-point inequality, but an inequality for involving infinitely many points. And you should think of these points in the Umbel position. So you have a specific point here, W, a branching point Z, and then you have all these infinitely many points there, Xi's, that you can think of them as the tip of the pedicel. So this is what an Umbel look like in nature. So that's why we decided to call this the Umbel inequality. And so here is the inequality that plays the role of the 4-point fork inequality for Markov convexity. Okay. So you have infinitely many points. So you have omega, Z, and these infinitely many points. And what we're trying to look at is to prove such an inequality here. Okay. So what is this about? So here, you're taking an average between this distance here and the supremum of this distance, these distances in green. Okay. So here we cannot take an average over everything because you have infinitely many quantities. So we take an average between this distance and the supremum here of all these distances. And on the right-hand side, we compare this to the infimum of all these distances in blue. Okay. Now, there is this term in the middle here, right? If you remove this term, the inequality is trivial just by triangle inequality and convexity. It's trivial. So what makes this inequality non-trivial is this term that you squeeze in between there. Okay? And again, you could put something simpler here, but here we want the lim inf because we had to prove that reflexivity is implied by Umbel convexity. Okay. So the fork inequality that Mendel and Auer used, well, you have only 4 points like this, and you compare a convex combination of these 3 distances there with the average of distances here. Okay. So, and as I said, we don't have this parallelogram inequality, but we were able anyway to go directly from the information that we have on the modulus of property beta directly to this inequality here. Okay, so there is no intermediate step here. We go directly from the modulus to this P-Umbel inequality. Okay. All right. Now, Umbel convexity is the strongest possible metric invariant we could prove because we had this renorming theorem in mind. Now, if your only concern is to show distortion lower bounds or estimate for compression rates, you actually want to have the weakest possible inequality that will give you these lower bounds, okay? Why do you want the weakest possible inequality? Because if you have the weakest possible inequality, it's very likely that you're gonna be able to verify this inequality for a much bigger class of metric spaces, okay? And if you want an obstruction, you want to know the largest possible class into which you have an obstruction to embed the Cotype branching trees. So going to the other end of the spectrum, we came up with this notion of that we call Umbel cotype. So here I just reproduce the definition of Umbel convexity so that I can compare it with the notion of Umbel cotype P. So why is this inequality significantly weaker than this one? So it's weaker because first on the right-hand side, I have the Lipschitz constant of F. And this is clearly less than the Lipschitz constant of F because this is less than the Lipschitz constant. And then you take an average. Okay, so this quantity is obviously weaker than this one. I mean, stronger than this one. And on the left-hand side, what is the difference? So we keep the sum here over the scale because let me remind you that this sum is crucial if you want to have estimates for compression rates. If you don't have this sum, okay, fine, you have something weaker, but then it can only tell you something about bi-Lipschitz embeddings. So here you want this sum, but then we had this average over all the levels and taking this infimum. So here we replace this by just a simple infimum over pretty much all the points in the tree, okay? And here we had this inf, lim-inf, and inf that was necessary for us to prove reflexivity. If reflexivity is not your concern anymore, you can replace this by just these two infimum here, which is actually more natural, where you're looking at, so you have a point, a vertex, and then you look at two neighbors that are distinct, okay? So you don't want to go in the same direction. So you take an infimum over I different from J, so you go into two different directions, and then you just take an infimum over all the points that form the form, okay? So this inequality is much weaker than this one, okay? But still, it's enough to give you everything you wanted. So to give you this lower bound on the distortion, it's still the right order of growth, and to give you this condition, this restriction on coarse embeddings of trees. Okay? Now, why is this interesting to have this much weaker notion? Because it's going to be easier. I mean, if you give me a metric space, it's going to be easier for me to verify that the space has this property and not Umbel convexity. Okay, it's a much weaker requirement. And let me give you an example of why this becomes very interesting. So the example is when you try to embed trees into Heisenberg groups. So you don't have to know much about Heisenberg groups. For us, it's just going to be a metric space with some specific metric. So here I'm looking at an infinite dimensional Heisenberg group, okay? So take Hilbert space, right? And so this is actually an abelian group, right, with the addition. And then we define a group operation on this Cartesian product. So L2 cross L2 cross R. And this is the group addition. So the group addition, well, you just add the first coordinates, you add the second coordinates, you add the third coordinates. So if this term is not here, this is just the basic sum. So it's just a basic sum of Banach spaces. Now, if you introduce this term here, so this is the scalar product, right, between vectors. So when you introduce this term here, then this group operation becomes non-commutative, okay? So you have non-commutativity. And this non-commutativity part is going to make a lot of difference in the geometric behavior of a metric that you can put on this group, okay? So the Heisenberg group over L2, so the infinite dimensional Heisenberg group, is just this set equipped with this group operation. Now, this group can be equipped with a metric, which is the Carnot-Caradeo metric, and we will denote this by DCC, okay? Now, I'm not going to tell you how this metric is defined for us. Just you have a group that has a metric that is left invariant and things like that, okay? Now, Schonli computed the Markov convexity for the infinite dimensional Heisenberg group, right? And what he showed is the following. He showed that the infinite dimensional Heisenberg group is Markov 4 convex and not Markov P convex for any P strictly less than 4, right? And so the Hilbert space is Markov 2 convex, okay? The Hilbert space is Markov 2 convex. Now, when you take the Heisenberg group over the Hilbert space, you lose a little bit on the Markov convexity, okay? Because it's only Markov 4 convex and nothing better, right? Now, this tells you that when you try to embed the binary trees into the infinite dimensional Heisenberg group, the Markov 4 convexity tells you that the lower bound is at least log of k to the 1/4, right? Now, the Heisenberg group over L2 contains actually a copy of L2. So you have the following upper bound, because we know that we can embed the binary trees into L2 with distortion square root of log k. And so there is a gap here. There is a gap between the lower bound and the upper bound. Now, Sean actually closed the gap immediately, and he said, well, the right order of growth is actually square root of log k, which I think was a bit surprising, because Markov convexity for Banach spaces, when you try to embed binary trees into Banach spaces, captures the right order of growth. Now, when you go to these metric spaces that are a little bit more general, Markov convexity is not able to pick up the right order of growth here, okay? So Sean had to use a different argument to show this lower bound here, right? Now with Chris, we try to compute what could be the value of our metric invariance for the infinite dimensional Heisenberg group. And we couldn't actually compute the Umbel convexity constant, okay? And but we were able to compute the Umbel cotype, because it's easier to compute the Umbel cotype, okay? So this Umbel convexity that you can upgrade to the full-fledged inequality is actually weaker. And so we showed that the infinite dimensional Heisenberg group has Umbel cotype 2, okay, and not 4, okay. So this tells you that when you try to embed the Cotype branching trees into the infinite dimensional Heisenberg group, you get square root of log k. And well, again, the Bourgain's argument tells you that it's the upper bound is square root of log k. So this lower bound, of course, it follows from this one, right? Because the Cotype branching trees contains the binary trees. But here we have a metric invariant that picks up the right order of growth. Okay, something that Markov convexity cannot do. So then when you have this, then you want to revisit the local theory, and you want to look at this invariant of Umbel cotype. Of course, you can define it. You defined it for the binary trees and not for the Cotype branching trees. And then maybe you would expect that this local version of Umbel cotype would be able to pick up the right order of growth, but we still don't know. Because here, the fact that this space has Umbel cotype 2 uses some infinite dimensional argument, okay? And actually, we can do something. So this is just one example. We can actually compute, so the most general result is that if you take the Heisenberg group over a Banach space with property beta p, so you can make sense of that, then this Heisenberg group has Umbel cotype p. Okay, so this is just one particular case of a much more general result. Okay, and I think my time is up, so I'll stop, and I'll be happy to take any questions.
Thank you so much, Florent. Go ahead, Kidon.
What is the relation between Umbel cotype P and cotype P for Banach spaces?
Between Umbel cotype and cotype?
Yeah, and also with nonlinear cotype. What is the relation with metric cotype?
Yes, so Okay, so we have a couple of results in this direction. So this so Markov convexity will imply this the Umbel cotype for binary trees. Okay, and this will imply also the Umbel cotype. So the local notions will imply the asymptotic notions.
Okay.
Now, for Cotype, well, I don't know.
It may be that this is another notion of nonlinear cotype, which, you know, the test is to show that it coincides with usual cotype for Banach space.
Yes, so the reason we called it cotype is because it behaves really like a nonlinear notion of cotype, in the sense that if you have trivial, let's say, Umbel cotype here, you would be able to embed the trees almost isometrically. The problem here with the trees is that you don't have the, I mean, it's related to this dichotomy theory, right? But you don't have the you don't have this multiplicativity of the constant in the case of trees.
You need the same P, of course. I'm asking if what I'm asking is whether, well, I guess that a Banach space of cotype P has Umbel cotype P?
No,
Even this is not true. This should be the easy direction.
no, because Umbel cotype still forbids
Right.
trees. So L1 would be a counterexample.
Right.
So it's not okay.
Yeah, no, it's right. Now, because here, I mean, Umbel cotype will now, of course, yeah, Umbel cotype will prevent the embeddability of trees. So yeah, so no, like it's a notion of cotype involving the geometry of trees. I mean, it behaves like cotype, but not for the Hamming cubes, right? For trees, but so it has different properties. Yeah.
Thank you.
Mm-hmm. Oh, I think there is a question in the chat that oh, Chris already answered. Perfect.
Hi, Florent, do you hear me?
Yes.
So thank you very much for this great talk. Congratulations. I was wondering, do you know an example of a P-Umbel convex metric space that does not cross-Lipschitz embed into any beta P Banach space? Like some kind of refinement of Kelton's counterexample.
So a beta. So say it again.
A P-Umbel metric space.
Right.
Or if I take it the positive way, does it cross-Lipschitz embed into beta P Banach space?
No, so okay, so what? Yeah, so what I forgot to say is that this Heisenberg group, for instance, you cannot embed them bilipschitzly into a Banach space with beta P. Okay, so they are Umbel, so they have Umbel cotype P, right? But they do not embed bilipschitz into a Banach space with property beta P, because beta implies reflexivity, and we know that this Heisenberg group, they do not embed bilipschitz to reflexive Banach spaces. Okay. Now the thing is, we don't know if this Heisenberg group they are Umbel to convex. We can only show that they have Umbel cotype P. Okay. Right, but it's for bilipschitz embeddings. I mean, course if she's here, does it make a problem? Is there a problem? I don't know, but this is, I mean, this is an important point. Like this Heisenberg group, they actually do not by Lipschitz embed into a Banach space with beta p. Otherwise, you would get this for free, right? So,
Okay.
yes, but to answer your questions, I'm not sure. I'm not sure. But there is a lot to be, there's a lot more to be done in this direction. And the problem that we have with the renorming is that we're lacking some linear results, definitely. We're lacking of a renorming theory for Banach spaces with property beta that does not go through AUS or AUC. So there is a lot to be done in the nonlinear theory, but also in the linear theory. I think we're missing some tools, for sure. But you have this whole scale of inequalities and that have different properties, and I think this is interesting. Like this deterministic inequality, you have a large range of inequalities that you can work with.
Okay, thank you very much.
Thank you. Any others? So if you compute James space, like what is the James space situation for either Cotype, Umbel Cotype, or convexity? Like what do you get there?
No, but I mean, well, Umbel convexity will imply reflexivity. So James is out of the picture for this. Now, Umbel Cotype, well, that's a good point. We don't know if Umbel Cotype implies reflexivity. I mean, the proof doesn't work. No, it doesn't mean that.
Does James space have it though?
But James, no, we don't know. We haven't tried to compute this for James.
Because if that's true, then it could maybe give like a non-coarse embeddability of C0 into James space or something like that. Because the James space proof, the Carlton's proof, is very non-local. So if there's a chance there, it might be interesting.
No, yes, we haven't tried to compute it for James space, but yeah.
Okay.
Oh, there's more questions. Chris is answering all the questions in the chat. That's perfect. I don't have to do anything.
Okay, any other questions here for Florent? All right, if not, thank you so much again for a very nice talk.
Thank you.